Hey everyone, and welcome to The Explainer. Today, we're diving into something that is honestly a total game changer for our digital infrastructure. We're moving away from static AI chatbots, the ones that just talk to us, and we're entering the wild era of dynamic AI agents, systems that actually take autonomous, real-world action. We're unpacking a comprehensive survey on how to make these highly capable systems trustworthy, and I've got to tell you, the stakes could literally not be higher. This isn't just some minor software update we're talking about. It's a fundamental rewiring of how complex work gets done. Basically, we're handing over the keys to our data and our critical operations. So, think about this for a second. What actually happens when an AI doesn't just write text, but clicks, codes, and acts entirely on its own? It's a fascinating reality, right? But also, let's be honest, it's a slightly terrifying one. Just let that sink in. When an AI can autonomously explore environments, log into your accounts, and execute complex, multi-step tasks without needing your constant approval, well, the blast radius of a mistake goes from a badly written paragraph to, say, a deleted enterprise database. The potential for catastrophic failure scales right up there with its utility. All right, let's pin down exactly what we mean by agentic AI. We're talking about an AI system that has persistent objectives. It can perceive its environment, plan out multiple steps, act using external tools, reflect on the outcomes, and then learn from the whole experience. This level of autonomy is exactly what transforms AI from a simple productivity aid, like a glorified spell checker, into a central node of modern digital infrastructure. Instead of just fixing your grammar, it's now managing your enterprise cloud servers, executing complex financial trades, or auditing thousands of employee records autonomously. But of course, with that massive power comes a totally new, completely uncharted risk profile. To really ground this idea, let's look at a very real and, honestly, very scary example from our source material called EchoLeak. This was a zero-click prompt injection vulnerability discovered in Microsoft 365 Copilot. Now, what makes this so alarming is how a zero-click attack actually works in practice. Imagine you have an agent tasked with just automatically sorting your corporate inbox. A hacker sends an email with malicious instructions hidden invisibly in the text layout. When the agent reads the email simply to categorize it, it accidentally absorbs those hidden instructions, and suddenly, it starts forwarding your proprietary company data to an external server. No one explicitly clicked a bad link. The user didn't make a single mistake. The agent was just doing its job, processing untrusted data, and it acted on it. This perfectly illustrates why figuring out agentic AI trustworthiness is absolutely crucial right now. Okay, let's dive into this. Here is our roadmap. First, beyond chat. Second, the risks of autonomy. Third, the agent workflow. Fourth, defending the system. And finally, evaluating trust. Section 1. Beyond chat. Meet agentic AI. Let's establish the hard line between AI that just talks and AI that actually does. So, on one hand, we have chat-based large language models. These are your static, single-turn text generators. You ask a chatbot for a dinner recipe, it spits out a list of ingredients, and boom, the conversation is over. The risk is completely bounded by that single text box. But on the flip side, agentic systems are autonomous, multi-step, and they actively use tools. Instead of just handing you a recipe, an agentic system browses recipes online, checks your connected smart pantry for inventory, uses your credit card to order the missing groceries, and then emails calendar invites to your friends. It produces a complex trajectory of intermediate states. Every single step it takes, every plan it makes, directly impacts real-world outcomes. The boundary between answering a simple question and executing a command just completely blurs. Moving right along to Section 2, the risks of autonomy, new failure modes. When we hand over the keys to external tools and APIs, we introduce some incredibly severe new risks. With this expanded attack surface, we aren't just worried about a system generating, inappropriate text anymore. Now we're dealing with prompt injection completely hijacking the system's goals, external tool misuse, and silent data exfiltration. But the absolute most critical, insidious concept here is what we call cascading errors. Because these agents operate over long horizons with only intermittent human oversight, what happens if the agent hallucinates just a tiny bit on step 1? Imagine it misinterprets a command, pulls the wrong user ID from a database, and then confidently applies that incorrect ID through 20 subsequent API calls. A minor misunderstanding snowballs into a massive, irreversible mess, all because there isn't a human in the loop double-checking every single action. Which brings us to Section 3, the agent workflow. Perceive to learn. This right here is the architectural battleground where these autonomous threats have to be neutralized. Now, what's really interesting about this architecture is how it maps out the entire lifecycle. It's totally crucial for understanding how we secure these systems. Think about how the control flows. You start with human oversight, which feeds goals and constraints into the core agent system. Now consider the internal components. You've got the memory module, which allows the agent to recall past actions, user preferences, and context. Below that, the world model acts almost like the agent's imagination. It allows the agent to simulate candidate plans, essentially asking itself, hey, if I do X, will Y happen, before it ever commits to a real action. Once it decides on a safe path, it sends a tool call out to the external environment. And then the environment responds with an outcome or observation, which loops right back into the system so the agent can course correct. It's a continuous, highly dynamic cycle of reasoning and acting. We can actually break that whole architecture down into 5 chronological stages. Let's weave a simple hypothetical task through this loop, like booking a business flight. First, the agent must perceive the state of the environment. It reads your calendar and sees you have an upcoming conference in London. Second, it plans. It decomposes that big overarching goal into finding flights, checking company budgets, and reserving a hotel. Third, it acts. It invokes the airline's API to actually purchase the ticket using corporate funds. Fourth, it reflects on the outcome, say, checking the email receipt to ensure the dates and locations are spot on. And fifth, it learns. It updates its internal memory, noting that, hey, you prefer morning flights for future bookings. By slicing the architecture into these 5 specific stages, developers know exactly where to install their security defenses. Section 4. Defending the system. 2 core dimensions. To protect this 5-stage workflow, researchers focus on 2 distinct areas. First up, let's talk about safety and robustness. This dimension is all about making sure the agent doesn't break itself or cause absolute chaos in its environment. Across those 5 stages we just went through, mitigations include things like adversarial training during the perceive stage. In simple terms, this means developers actively attack the AI during its development with tricky, malicious prompts. It's sort of like a digital fire drill, so the system learns to recognize and ignore those attacks in the real world. We also see strategies for handling out-of-distribution inputs. These are bizarre, completely unexpected situations the AI has literally never encountered before. Safe planning constraints ensure that when the AI gets confused by something completely weird, it doesn't just wildly guess and start clicking buttons. Instead, it falls back on strict, predefined behavioral boundaries. The second dimension is privacy and system security. Here, the focus shifts to protecting the actual data and the underlying infrastructure. During the perceive stage, we see methods like zero trust intake. Basically, the system assumes every single piece of external input is potentially hostile and sanitizes it immediately. Then, when the agent moves to the act stage, the system utilizes strict data loss prevention or DLP filtering. Imagine your agent is tasked with summarizing a highly sensitive internal coding project. Without DLP, it might decide the absolute easiest way to solve a bug is to accidentally copy and paste your proprietary code blocks right into a public search engine. Yikes, right? DLP acts as a hard security checkpoint, recognizing the shape of sensitive corporate data and blocking it before it ever leaves your internal network. And this brilliantly illustrates how we can map specific defense hooks directly to the stages they protect, creating a really comprehensive shield. In the perceive stage, we use validation hooks, like strict input filters, to catch malicious code right at the door. In the plan stage, we use verification hooks, running logic checks to make sure the agent's proposed steps don't violate any core constraints. When it comes time to act, we rely on safeguards. Tool sandboxing is the ultimate safeguard here. Why? Because even if an agent goes completely rogue, a sandbox ensures it is trapped in a simulated or restricted environment where it can't actually delete real user files or blast out thousands of real emails. The reflect stage uses diagnostics to catch anomalous behavior in real time. And across the whole shebang, logging ensures we have a continuous, tamper-evident audit trail of every single thought and action. Finally, Section 5. Evaluating trust beyond the output. Because we have to ask, how do researchers actually test if these hooks are holding up in high-stakes environments? The crucial takeaway here is that you can no longer just judge an AI by its final output. If a regular chatbot gives you a good answer to a trivia question, great, you trust it. But if an agent successfully completes a complex task, you still have to ask, wait, how exactly did it get there? We have to rigorously evaluate the entire multi-step process. Reviewers look at process signals like constraint violations. For example, did the agent temporarily breach a firewall policy during step 3, even if it managed to fix the issue by step 10? That is a failure of trust. They look at trace completeness. Is there a suspicious gap in the audit log where the agent did something undocumented? A successful final outcome means absolutely nothing if the agent violated a privacy policy or compromised security along the way to achieve it. Which brings us to this incredibly powerful paradigm shift from the research. Trustworthiness must be assessed at the system level beyond single-turn outputs. As we invite these autonomous agents into our businesses, our critical infrastructure, and our daily lives, we have to fundamentally raise our standards. We have to demand system-level assurance. So I'll leave you with this. The next time an AI assistant offers to take over and handle a complex multi-step task for you, ask yourself, do you just trust the final answer it gives you, or do you actually trust the entire hidden process it took to get there? Thanks for joining me on this explainer. Keep questioning and keep learning.